Hello everyone, here is the last video in chapter 5, the gas laws, and that's called the kinetic molecular theory. And kinetic molecular theory was what this video is about, and basically what it says is this is the kinetic molecular theory, or the KMT, as it applies to gases. So the KMT explains a lot, but when it applies to gases, what it does is it explains why gases do what they do. So there's actually 4 points to the KMT, and you can read them just like I can. So I'm just going to explain them as we go. The first one says the particles are constantly moving. No matter what, gas particles are constantly moving. The only time they really stop is at absolute zero. And because they move, this gives them the chance to expand, to diffuse, to effuse, to do all sorts of things. So the gases generally move away from each other because the attractive particles are very weak, or very small. So I'm just jump to number 3. The attractive repulsive forces between gas particles are negligible. And actually, this is the part that's going to get us in the most trouble as we go on with the course, because gases do attract each other, although it's very, very negligible. And this has to do with their polarity. Okay, so gas particles are actually quite they basically ignore each other and would rather drift away. According to part 1, the particles are in constant motion. Number 2 says they're extremely small. Now I hit this point I've hit several times over the course of these videos in chapter 5, and that's the particles are extremely small compared to the size of the spaces between them. There's a super small volume of actual gas particles because they're so teeny tiny. And we have tremendously large spaces between them, and that means the gases can typically be compressed. The number 4 says collisions are elastic. In other words, there's no net loss of average energy during the collisions. Gas particles keep bouncing and they never slow down. Okay, only as long as temperature stays constant. So as the gas particles collide with themselves or the sides of the container, it's not like they slow down because they've lost energy. And if they lose energy, that means that if you blow up a balloon, it would slowly deflate in front of your eyes because the particles would lose energy and lose motion. They don't. The collisions are elastic. They keep their energy, they keep their motion, and the balloon stays blown up for days. Okay? Average kinetic energy is directly proportional. I say equal, but that's more or less directly proportional to average temperature. So if they're moving, if I have 5 gas samples and they're all at 25 degrees Celsius, which is room temperature, then I can say that their average kinetic energy is actually the same. Okay? So average kinetic energy is directly proportional to the average temperature. So if you were to ever say, well, I have 2 gases and they're at one's double the temperature, double the Kelvin temperature actually, what about their energies? Well, I would say the one that has double the temperature, the Kelvin temperature, has double the energy that the colder one has. Okay, so if we have this particular situation, then if a gas obeys all 5 points to the KMT, the kinetic molecular theory, we're going to call that an ideal gas. Okay, we will treat the gases in this chapter as ideal. Okay, as a matter of fact, in general chemistry, we treat all gases as ideal. Okay, we assume that they fit or have obey all 5 points of the kinetic molecular theory. So when we talk about a real gas, how does a real gas deviate from the ideal gas law? The ideal gas in the kinetic molecular theory. Again, ideal gases obey all 5 points of the KMT, but real gases deviate in some way, and that deviation happens in point number, I think it was 3, where there is some attractive force. But now I say the truth here is that the deviation is so slight that we treat all gases under standard conditions. Notice standard conditions is not STP, so just be careful. Standard conditions is 1 atmosphere and 25 degrees Celsius. We just treat them as ideal. So the best conditions for a real gas, by the way, down here, if you want to pay attention to this, is that we want to have the best way to get a real gas to behave like an ideal gas is to get the temperature really, really hot, so they're moving like crazy because they have high energy now. Remember, temperature and kinetic energy are directly proportional. And we don't squeeze them at all. We let them have the least amount of pressure applied. Now they won't, because remember, if you squeeze a gas, now they have to pay attention to each other because they're closer. So if we alleviate all pressure, and we jack up the temperature really high, then every gas acts as more or less, every real gas acts more or like an ideal gas. Okay? So let's see here. Oh, here's some other things. Real gases deviate from ideal gas behavior because intermolecular forces that cause gas particles to be attracted to each other. So how do we, what's the worst way we can make, how do we make a really real gas? We really pack a lot of particles in there, in other words, high concentrations of gases, or the N, the number of moles, is very high. We squeeze the heck out of them, or we apply an extremely high pressure, and we make them really cold so they're barely moving. Okay, that's how we get a real gas. That's the opposite of what I was talking about. Okay, so let me take a look at this one right here. You have three samples of gas. You have HCl at 298. You have H2 at 298. You have O2 at 350. Compare the average kinetic energy of the particles, the molecules in the three gases. Okay, so the average kinetic energy is, remember, kinetic energy is directly proportional to temperature. So I would say that the average kinetic energy of the HCl and the H2 is going to be relatively the same. The average. The O2 is going to be will have the highest amount of energy because they have the highest temperature applied to them. Okay. Now, this is called a Maxwell-Boltzmann energy distribution diagram. Boy, that was a mouthful. And basically what this says is as hot particles, or particles at higher temperatures, in other words, the red line here, the hot particles actually spread out. Okay? So if you take a look at what we have here, let me get rid of this. These warm particles, things at 1,000 K, are really spread out on our graph. Now, why is that? Okay, because now we have particles moving at a high temperature, therefore they have a greater molecular speed. The average number of particles, you'll notice the peak is lower. The peak is lower than colder particles. The reason for this is the probability of positions they can take under the curve. Okay, now that's kind of weird, so let me talk about that. You'll notice that as you get to hot particles, they spread out long ways, whereas cold particles are more contracted or more compressed into a small, tight bell curve. The reason is this is as we heat up particles, they can take more positions under the bell curve. And what that means is you not only do you have these energies here, these temperatures here, but now you have these out here. So these particles are screaming super hot, but these particles are almost frozen solid. So again, hot particles have a short, squatty, spread out bell curve, whereas the cold particles now, again, when you get to cold, we have a different situation. See, there's no ceiling to hotness. There is a basement to coldness, though. There's the lowest you can go, and that's absolute zero. So as you get colder, you keep compressing the particles more and more into a skinny little bell curve. So as you have this skinny little bell curve, it keeps getting taller and taller because there's less probability of position in the molecular speed. So the particles don't have an almost infinite amount of particles because they're stuck here and here. So these are the hottest particles here. These are the coldest particles here. The average is there. This says the average is here. Now notice it's the average. I keep mentioning this word average. When we talk about temperature, we're never talking about the energy of a specific molecule. We talk about the collection of temperatures, and that's called the average. So we find the average here, 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 and here of any bell curve. Okay? Where most of the particles, if I take a look at the red line, most of the particles, and I'm just arbitrarily doing this, fall under the average plus or minus some portion of it. Okay? So that's a Maxwell-Boltzmann energy distribution diagram. One of the last things we'll talk about is something called root mean square velocity, and all this says is I just want you to understand that this is a constant, and if I keep temperature constant between two gases, now I'm going to take a look at the bottom here, and the bottom is molar mass. That's molar mass. So what this means is that heavy particles, which means a greater denominator, move slower. They have a slower velocity. Okay? So notice the energy is exactly the same because the temperature we're keeping constant. The temperature is constant, so the kinetic energy is identical. So let me look at this one. Let's look at this one step further. So if I have V RMS, the root mean square velocity, of 3RT, and we'll say temperature is constant, over the molar mass of hydrogen, which is 2 grams per mole, versus the VRMS, or the root mean square velocity, of 3R, which is our constant, temperature is constant, but now we're going to use methane, which is 16 grams per mole. Okay? Notice This denominator under the same numerator on both sides is bigger, causing our VRMS is going to be lower. They will have less velocity even though their energies are exactly the same. This denominator being smaller will cause this number to be higher. So again, small particles have a greater velocity. Heavy particles have a lesser velocity. Okay? And this is assuming that the temperatures of those two samples of gases is exactly the same. Okay? Thus, their energy is exactly the same. Okay, I believe that's all I have. Let's see what's on here. Okay, that's another consideration. List the particles in order of increasing speed. Real simple, increasing speed is the heaviest one. HCl has a molar mass of 36.5. This is 2, and this is 32. So list them in order of increasing speed. This is the slowest, this is medium, and this is way faster. Draw a molecular distribution graph and represent all three graphs with curves. So energy distribution diagram says these are the number of particles. This is the meters per second. So we're going to have our H2 is going to be our flat line. Our O2 is going to be somewhat of a skinny line. And the HCl is going to be higher and taller and even skinnier. Okay? So that's that's taking a look at the meters per second, or the velocity of these particles. Okay, I'm done. So that's the chapter. Let me know if you have any questions, and we will get to this in class. So thank you for your